Welcome to notes number 3, the scientific method, part 1. Purpose of these notes is to give one general overview introduction to the scientific method. So again, if we're going back to our analogy of it being a cultural, looking at science as a culture, this is just us first getting to know the culture a little bit and the key parts of what is the scientific method. So we'll be covering things such as empirical evidence, cause and effect, causal relationships and causality, and then the basic steps of the scientific method. In the scientific method part 2 and 3, we'll dig deeper and add more terminology and more understanding into how does this process work and how can innovation come out of it. Now, to begin with, the scientific method, you can see the definition here. And we're going to have a couple different definitions for this, and we'll keep digging deeper with it. But it's a procedure that has characterized natural science in the 17th century, consisting in systematic observation, measurement, and experiment, and formulation, testing, and modification of hypotheses. Now, within this definition, there's a lot of key words then that you need to pick up on. One being procedure, that this is a systematic sequence of steps that can be fluid. You also have observation, measurement, experiment, hypothesis, testing, and modifying throughout this entire actual process. So these are some of the key terms you need to dig deeper into to understand this actual method, understand how does it work. And this, as a method itself, is ingrained into all forms of actual science, and that science thinking, that ever continual kind of evolution and growth and change of knowledge as new knowledge comes into place. So when conducting research, scientists use the scientific method to collect measurable empirical evidence in an experiment related to hypotheses. Often these hypotheses come in the form of if-then statements, and the results aiming to support or contradict a hypothesis, not to prove it. So within here, you'll see the highlighted empirical evidence word. Now that's important. There's evidence just in general you can get, but what does it mean for empirical evidence? The next slide will go over a deeper definition of that. But we can sum it up now, being that measurable part is a key part of it. And the other part of the scientific method is that we're not doing these to prove our hypothesis, is that we have a question, we have a hypothesis where we think this could be a possible answer for it, and we want to gather data separate from ourselves and analyze to see, okay, based upon what has actually been observed that I've done, can I accept or reject the hypothesis that I have found as a logical final step from it? So I'm never trying to start from the get-go to say, okay, here's my hypothesis, I'm going to set up an experiment to prove it, which is already presuming truth, which is not leaving it open that it's testable and falsifiable. So empirical evidence is measurable information acquired by observation or experimentation. Scientists record and analyze this data. The process is a central part of the actual method. So key here is the fact, measurable. This is something that you have to use some kind of actual tool to get a number back with a unit associated with it. And that is the basis of all these evidence. No matter what we're looking at, it has to fall under this empirical evidence of, okay, I've observed it, I have taken a measurement, I have quantified it in some way. And also it came from the experimentation phase. Now, with empirical evidence, you and I can go about measuring and observing these, but other people also have to be able to do the same measurements and same observations and come out that we accept that this should be similar. And this includes that we each agree upon how things are being measured and how they're actually being observed. So inches to centimeters, all these things not being presumptuous, but knowing, okay, clearly communicating, this is how I've observed it, this is how I've measured it, this is the tool that I've actually used, so that someone else can go and do that, and they can also verify that data. And that's going to be important when you have that evidence. It's not just me making this claim, is I can say, well, here's my argument, here's the evidence I found for it, and these are the measurements, and this is how I went about doing this. And then you can also then try to verify that yourself in doing similar things. So examples of empirical evidence is things like speed of a train, length of the train, and the number of people on the train. These are all things that are measurable that can turn into an actual quantity. We'd have to communicate, well, how are we measuring speed and what is the unit? And the same thing with length and with the number of people, quantifying that. So another more specific example is, say, an observation or empirical evidence that was gathered, say, is like the rock has a mass of 150 grams. When released, the rock falls at a perpendicular path to the ground. It took 1.5 seconds to reach the ground. And you can get that feel right there of that empirical evidence. This is a number, that this is quantifiable, and someone else can then go same way and do that same work. And so whatever we do in all of the scientific method and throughout whatever argument in science, the basis of everything from that is this empirical evidence. That it'll come down to taking these measurements, recording these, and then analyzing it. And any final conclusions that I come to accept or reject the hypothesis are based upon this evidence. The other key thing for all stuff in science is, and to get used to with the scientific method, is cause and effect relationships. This is going to be the basis for every single question you're dealing with, built into the entire process of the scientific method, and how we're trying to look at the world if we're coming at it from a science cultural perspective. So, scientists design an experiment so that they can observe or measure if changes to one thing cause something else to vary in a repeatable way. And so you have to kind of think of these as you have a cause as being event. There's two events, one preceding, one following after. So event 1, event 2, and they're linked together that one is the cause, so some action that's happening, and the other one is the effect that came after because of the actual cause. So example here is like cause, raining, why it started raining. Effect, what happened? Oh, I needed an umbrella. Maybe the two things. So I'm wearing I have an umbrella now. It's the effect because the cause was it started raining. So, cause and effect. When one event causes another to happen, the cause is why it happens, the effect is what happens. And this is going to be important, and we're going to get back to this. It's going to tie into your empirical evidence that right now we're talking very vague about these events, but whatever it is within your question, you're looking at this, and we're going to end up having to quantify this. So in Scientific Method Part 2 notes, we'll go deeper into this, talk about things like variables and measurements. So, scientists try to figure out how the natural world works, and doing so, they use experiments to search for cause and effect relationships. So generally, we're trying to ask a question. We saw that in the previous ones. I want to ask a question, and then really built into that question is a cause and effect relationship. And we have to identify, okay, well, based on our question, what is the cause and what is the effect that we're looking at, and narrow that down and do some research. Because cause and effect relationships explain why things happen. If we understand this, if we understand that, okay, well, this is the effect and this is the cause, then we can start designing things around that. We can know more things around the world, but then we can start taking advantage of, okay, I know if I do event 1, and it's going to cause event 2 to actually happen in some kind of fashion. And what can we design and change and maybe make the world around us better, or make some changes, or just answer different questions. It's up to that innovation side that comes after. So, in some cases, cause and effects are straightforward. We know this. One event to the other. In other cases, cause and effect relationships are more complex and less apparent and hard to see. And this is the difficulty of we can't always have an exact answer, but it takes that time and more questions being asked. More new knowledge being generated out of the scientific method and the process that people are going through. And and once we know this, it changes maybe the knowledge that we have within the future, and we can start digging deeper and understanding the complexity between this cause and effect. So part of understanding cause and effect relationship is seeking an answer to the questions, how does it work? Being the mechanism in the relationship, or what happens and why does it happen? So explaining the actual relationship. So if you're looking at questions, they come out being this how and what and different ways from this actual process. And so in that beginning phase of anything we're doing, as we saw in the previous set of notes, is it's about asking those questions. And if we can start being more about how, why, what, and then looking deeper into causes and effects, we can start designing, going through the rest of the actual process. So science examples from here. So if we take specifically the category of ocean scientists, there's many different cause and effects relationships that people could be looking into that, depending on the area they're at. So if it's, say, ocean scientist relation to climate, could be seeking to understand the cause of global change, like the causes of global climate change and the effects it has on the chemistry of the ocean. Now there you can see between climate, something maybe we can measure the cause that would have as that preceder effect or event, and they have the effect afterwards. Okay, how does the chemistry, something measurable also from the ocean, change? And then because of that change, maybe that affects other things that are going on in the actual ocean. Say marine biologists may study what causes organisms such as fish or whales to suddenly and unexpectedly die. That there's the effect of, okay, well, they're dying. What was the cause before, and searching backwards and seeing, maybe researching what's happening. Or in the case even engineers, following from this, is that engineers, maybe to design a new submarine, they have to apply an understanding the effects of the depth of pressure. Now, between all this, we're talking about cause and effect, being event 1 being an effect on event 2. Now, that's two different kind of objects as you can think about them. And we need to talk about a relationship. What could we have between them? And that's causality. The relationship between an established cause and effect. And so if we know there's event 1 causes event 2, there's a causality between the actual two of them. Also sometimes referred to as a causal relationship. So event 1 caused event 2. And beginning when we're asking questions, we probably think that we know about like a cause and effect. We don't know for sure. We think that there's maybe a possible causal relationship between the two. And what we need to do by the end argument, by the end of the actual scientific method, is to say, well, how have we established an argument to say that we believe there is a causal relationship between the two things that we were looking at? And then other people can review that. So beyond just the empirical evidence and the cause and effect, by the end of our argument, by doing the experiment, by going through the scientific method, we were trying to establish causality. Now, in notes scientific method part 2 and scientific method part 3, we'll be going more into depth of that, of like how do you start stepping through the scientific method and which parts of it are you using to set your argument, your basis for how causality is actually established. Now, causality, we can ask questions that will, again, we'll talk about this before, that will contain cause and effect relationships. And throughout all of this, we're trying to establish that causality relationship, so what I was just talking about. And this is all done based upon the empirical evidence that we have. So we have a cause and effect in our question. It's going to be the key part, and built into our hypothesis and our predictions. We're going to be going through an experiment and gathering that empirical evidence. So again, that measurable, observable evidence that other people can also verify. And we're using that evidence and analyzing it to then say, okay, well, do I have a causal relationship between our cause and effect by accepting or rejecting our actual hypothesis? Now, causality itself is also the study how one thing influences another. So cause leads to effect. And there's a couple assumptions you have to keep in place. We'll go through now, and also becomes important when you're trying to establish causality in your actual argument. By what are you writing down by going through the scientific method? What evidence have you gathered? And how have you set stuff up in your procedures to make sure that it's not something else that's actually the cause between your cause and effect, and your argument becomes stronger. So the first big assumption is that things have causes. They don't just happen on their own accord. So it means if you see one event, there's probably something before that in a chain that actually caused that. So example, if a ball moves, you're seeing that the likelihood is that maybe someone kicked it or someone threw it. If an apple falls from a tree, it's because maybe a wind came along and knocked it off, or the weight of the apple itself was so large that the stem couldn't hold it anymore and it broke free and fell. And so there was some kind of cause first that led to an actual effect. Second is that effects follow causes in a predictable, linear manner. So you swing your leg, make contact with the ball, and off it moves in that order and no other. This is if we're going through a linear view of causality of a chain of events of time of one to the next, to the next, to the next, if we stick with that specific view for this course. So you think of that previous, that it's always cause first and then it's the effect. Third is that big effects grow up from little ones. So if we're seeing lots of things, maybe there's multiple reasons for causes and things that we could dig deeper. So going into kind of a physics one, here's say like a piston. So something you see in a car, in an engine, for example, starts to move when a lot of individual hot atoms hit it against it and push it in a certain way. So in a car with the piston, gas is ignited, it explodes, hit the piston is moving down. So all those atoms from being ignited and that energy and that force shoving and moving the pistons. The laws of thermodynamics, which govern the way atoms move, then provide certain rules about what causes can precipitate what effects, and so an overall direction for causality. So a flow of time. So that explosion, atoms hitting it, piston going down, energy being transferred. So again, the scientific method. Cause and effect is the backbone of the scientific method combined with that empirical evidence. Throughout all the steps, there's always cause and effect. So if it's asking questions, if it's making your predictions, if it's designing stuff from your experiments and analyzing the data and coming to a conclusion, every single one of those steps includes the cause and effect that you were looking at from the very first step. And the fact that by going through the process, you were trying to set up this causal relationship and trying to prove causality. And so from here, like the job of the scientific method is to tell us if our cause produces an observed and actual effect. So this entire kind of step or procedure we're going through is also a way of building up an argument and having a systematical, logical way to step through and test and see, do we have that causal relationship? So when we come up to those notes shortly, you have to realize, again, that's key to everything else. Is remembering, again, empirical evidence and cause and effect is built in through the entire thing. So the scientific method is a process for experimentation that is used to explore observations and answer questions. Talked about in the beginning. So the first definition, given a more historical kind of definition, this is kind of keeping it deeper, is a process. Again, a systematic sequence of what you're doing. Now, does this mean that all scientists follow exactly this process? No, I'm giving you a basic introduction to it, and different forms of science will apply it in different ways. And the scientific method itself evolves and changes over time and innovates and grows from this process. But the general ideas and general steps of this are also still all within there. And so if you're going to critique, again, or understand the science culture, you've got to understand the scientific method. You've got to understand these overall steps of what you're going through and what happens. So for example, scientists studying how stars change as they age or how dinosaurs digest their food cannot fast forward a star's life by millions of years or run medical exams on feeding the dinosaurs to test their hypothesis. We just don't have access to be able to do those kind of actual measurements. So they will then have to modify how they're gathering this empirical evidence and combining it together. So dinosaurs may be looking at what was found around them, that timeline, other things. This is not my background. So you have to have that modification, but it's still within there, and there's still that scientific method. So, but even when it's modified, the goal remains the same, to discover cause and effect relationships. So establishing a causal relationship between event 1 and event 2 by asking questions, carefully gathering and examining the empirical evidence, and seeing if all the available information can be combined into a logical answer by the end. So again, not trying to, again, show that it's our truth. It's just that, okay, I had a question. Here's the cause and effect I have. Here's the procedure I went through. Here's empirical evidence and how I gathered it. And here's a final conclusion at the end and showing how I analyzed that and what did I come to, how did I come to that actual conclusion. And then others can read through that who have experience and they can critique it and they can build off of that and keep going from there. Whether you're doing science for a basic project or anything else, or hands-on, or questions, you're still doing this scientific method and you're working to make these observations and gathering data, answer questions as well as you possibly can for now, and add to that pool of growing scientific knowledge, not adding to the new truths, but the new knowledge that could change previous understanding, and knowing that maybe what you found now could also change in the future. And how can you grow and how can you innovate off of that new knowledge? It's not just immaculately grown out of something else. How did it build up from the previous steps, and how can we keep this growing and changing our understanding of the world around us? And then how can we use that to innovate and think in new ways, react in new ways? So even though the next slides and the next videos and stuff show the scientific method as a series of steps, keep in mind that new information and thinking can cause a scientist to back up and repeat steps at any point in time in the process and think in new ways. So even though there's steps, you may realize, oh wait, this is not working. We've got to stop and maybe go back and change our hypothesis. That the new information I found is showing like, no, I can't keep going with this and I got to restart the actual experiments or rechange the actual overall process. The idea is when you're going through this process, you're learning as you're actually going as well. Now here, first introduction, I like to do things in threes. So I don't want to just go through the scientific method just once. I want to give you a basic, quick introduction. That's what this video is for. Too long, didn't read, just want to see the video. And so you get a base here. So just the short video, it fits my personality just with the music. You'll see in a second. That I give you that first, okay, here's the steps. Okay, I understand this generally. Then I'm going to do a longer review of it. And at the end, then there's another video that then does another recap of everything and then adds a little bit more knowledge. And this gives you a chance, okay, well, while I'm watching this, taking notes, as hopefully you're doing and hopefully working through the actual questions that are not worth marks. Again, the questions you see for the slides we talked before are not worth marks. It is just to help you review and get notes, and then maybe for future tasks or assignments and exams that you can use that knowledge as a way to answer those better.
Have you ever had a question about the world? Like what plants need to grow? Or how to blow bigger bubbles? There is a way to find the answer to these and other questions that is used by scientists. It is called the scientific method. If you use it, you can be a scientist too. The scientific method is a way to ask and answer scientific questions by making observations and doing experiments. There are 6 simple steps to follow. First, ask a question or identify the problem you would like to solve. Second, make observations and do research about your topic. Observation means to study carefully. Once you have observed and researched your problem, you are ready for step 3. Form a hypothesis. A hypothesis is an educated guess about how something works. In order to be useful, a hypothesis needs to be testable. This means that you can actually test it and see whether it is true or not. After you have your hypothesis, move on to step 4. Design an experiment and test your hypothesis. When designing an experiment, you must be sure to only test one thing at once. You can do this by making sure to only change one thing or variable in each experiment. Everything else must remain the same. Once you have completed your experiment, analyze your data. To do this, you will look at the results of your experiment and try to figure out what it means. Finally, using your data, you can draw a conclusion. If your conclusion did not support or agree with your hypothesis, that's okay. It doesn't mean it was a bad experiment. Using the information from your first experiment, you may need to form a new hypothesis and create a new experiment to test it. Even if your conclusion does support your hypothesis, you may have a new question you'd like to test and can begin the scientific process all over again. The scientific method is a step-by-step way to solve problems and answer questions logically. Thanks to the scientific method, many important discoveries have been made about our world, but many unanswered questions remain. Would you like to help answer them? You can. Just remember to be scientific. Ask a question, make observations, form a hypothesis, design an experiment and test that hypothesis, analyze your data, and draw a conclusion.
So that video does a good job of summing up what I'm just about to go through and giving some more definitions to that. But also, always remember that if we look at science as a culture, what did you just see in those videos? If someone put this specifically together, maybe they had actual scientists, probably just had actors or stock videos for a lot of that, but what imagery was actually used? The white lab coats, the tools, the measurements they were doing, how did they do that? Always, when you're looking at these videos, you're trying to look at an actual culture, look at science, also realize how does that play a role? And also who is a scientist or who can view themselves, which is anybody really can. So, the scientific method. This is the full version, the longer version, however long this takes me to actually go through. And as we dig deeper, you're going to see that little diagram over there as kind of a way to view the actual procedure. And you should really get accustomed to this. I suggest maybe drawing it out yourself. If you're taking notes, I really suggest for each one of those steps, like asking a question, that bubble, maybe you should be adding extra notes off of that and keep coming back and reviewing this, because this is a key way to think about it. Kind of simplify it down, but just some kind of the steps and that progression of the entire method itself and what are you doing. And so if you have to critique or look at something else, you should be looking at, okay, well, how did they apply their use of the scientific method? And if they're writing about it, generally the writing it up goes in the same format of talking about their question, talking about the background research they had, talking about their hypothesis, how they set up their experiment, how they analyze the data, and then the final communication of those results and saying, do they accept or reject it? So when we later on go look at a case study, you should review back to this and see, well, have they kind of followed the same flow in their write-up? If you're going to go about designing and innovating off of a question in the beginning, when we get to that virtual reality and augmented reality, what is the question that you're asking? And if it's not augmented reality or virtual reality, whatever the main topic is that we're going through, like, what's the questions you have? What's the cause and effect? And you may not be experts in it, and you're just novice beginning growers, but doing that background research from there, and based upon that research and the questions you were thinking of, what are your hypotheses you could come from? And then how could you design an experiment to see if you can get empirical evidence to back up what you think? And maybe even while doing this process, you're coming up with new ideas, new ways to innovate and use that kind of concept, and digging deeper and building your quantitative and your reasoning skills and becoming stronger within that. Or maybe you're just thinking of new ways to critique this method. Maybe there's some other way of knowing and understanding the world around us. So, step 1, ask a question. Maybe bring out your inner child and not filter stuff out, but just ask questions. What is the question? What is something that you are curious about? And being free about this. So you start there. Start by asking questions and seeing what you observe. So questions like how, what, when, who, which, why, or where. And generally, the questions, though, that come through the scientific method that become easier is when you're thinking of something that's measurable within numbers. So to get that empirical evidence. So if you're looking at the questions and you're thinking about cause and effect, you have to think about, well, how could I measure these? And this also can be part of that background research. If you're not sure, maybe you need to do background research of how other people measured. What other tools, what other units were created, and ways to communicate and become accepted within that culture as that key form of, well, okay, this is how we measure stuff. So is it inches? Is it centimeters? Is it vice versa? And then sometimes if you realize there isn't a way, maybe that's a new thing you can innovate on. Maybe you're finding a way that you can make that standard measurement and how you come to that in a new scale, and then distributing that to others and seeing if that gets accepted and becomes that new dominant form of how things are actually measured, and innovating off of that actual process. So here, just ask questions. Why does that happen? Why is the sky blue? Why is it raining? Or digging deeper based upon previous knowledge that you actually know to get to deeper, more specific questions of what could actually happen at this time. That's the first step. So whatever you're doing, if it's coming to something new, just do some background research, and maybe then new questions will come out from there, and you dig deeper. But you look for that cause and effect within your actual questions. What are the events between the actual two? If why the sky is blue, well, that's event being an effect, so maybe there's a cause before that, and researching what was that actual cause between the actual events. So what are you looking at? What are you doing? Next, do that background research. So rather than starting from scratch and thinking like, I'm going to know everything, there's nothing beginning there, what a plan of answering a question like what has been done before. So talking to previous people, using the library and internet searches, and not just your own self-confirmational bias searches, but other information, maybe looking at other scientific journals and knowing which journals and which area and which people become that area. Okay, well, where can I build all this knowledge from? So doing your lit review or meta-analysis and beginning by looking for what's out there. I may have the beginning question, but I can use keywords from my question, the key things for my cause and effect, to research other papers and other work to see, hey, is the question I'm trying to answer, has it already been answered? If it has, how do I try to say that my argument's going to show a different way of answering that maybe contradicts or backs up that previous research? Who knows? But do that previous research. So start basic videos, keep digging deeper, keep adding new keywords that you find, and building off of that. Once you've done this research, and maybe you've had to go back and modify your question and what you're thinking, realize maybe this will work and doesn't work, or if it does, you go next and you want to construct your hypothesis. And so this is another key thing to say here, is that hypothesis is a key statement. You're going to see coming up words like educated guess, but you have to realize that's a very basic part of that definition, and you can't just leave it at the word saying educated guess from right here. You have to say, well, what else is added into it? And this is another key artifact of science culture and the scientific method, is this hypothesis, that we're taking that beginning question, the background research we have, and we're turning that into something more specific that we're trying to look at and that we're trying to actually test. And from this hypothesis, we're then building our predictions of what we think is an answer and not assuming any truth from that. And then based upon that, we design an experiment to hopefully remove our bias, remove other things we think that could be causing like whatever we're looking at within it, and then designing and gathering the empirical evidence, analyzing it, and only based upon the analysis of the actual empirical evidence do we then go back and say, okay, yes, this is strong enough that I will accept or reject the hypothesis. And this course will be a little bit vague about that line where you say accept or reject. Most times in other science forms, it's very specific that you can get down to calculations. You can say, well, no, this is, say, 40% out of 100%. No, this isn't strong enough. Versus say it's 80 to 95%. This is strong enough, we'll accept. Kind of like passing a course. 40%, not so happy. 50%, maybe. But as I get higher to 100%, it's all happier. Hey, I'm passing the course. Or whatever level that you set as a bar that is good for grades and yourself. So, saying here, the hypothesis is a tentative, testable answer to a scientific question. Once a scientist has a specific question they are interested in, the scientist reads up on what is already known on that topic to build it up. So it's a tentative answer. This is key part. So even being that education guess, tentative answer, they're still not saying it's the truth. It's just saying what I think I have now that I want to then test and gather data on and check back on. So they then use this information to form a tentative answer to their scientific question. Sometimes people refer to tentative answer as an educated guess, but keep in mind, though, that this hypothesis also has to be testable, since the next step in the experiment is to determine whether or not the hypothesis is right. So this is not assuming that it's true from the beginning, and that's why you don't say the words proving. If I see that when you're writing later, shows, well, you're not really understanding this culture. Saying that we're doing the experiment to prove our hypothesis? No, you're not. You're not showing a proper understanding of the actual science culture when it comes to hypothesis and experiments. It means, well, I want to test it to see if it passes or fails based upon the evidence they have, and trying to remove my objective side in this case and say, well, what does the evidence actually show? You may personally disagree with that, but here, if we're just trying to understand the science culture, that's what happens. This is the way it actually is. And so if you can critique it, maybe you come from different arguments of why that happens, but you need to understand this as a key part of what we're working through. So, hypothesis leads to one or more predictions that can then be tested by the actual experiment. So what I think is an answer, but then I make predictions of what will come out of that, and often these take the form of if, cause, then effect, specifically what you're looking for. And why that's important as being testable is if-then statements. It means, well, if this happens, I'm going to see this happen. Then based on the evidence, if the part after the then doesn't happen, the whole prediction's not right. And then we'll say that we will not accept this, we'll reject it. And so you can see these next kind of steps of going through that. We've had the question, we've had the background research, we're making hypothesis, we're making the predictions. You're seeing that step-by-step way of building and going through to answer your question. So predictions should include both the cause and effect you're looking at. A single hypothesis can lead to multiple predictions, but generally 1 or 2 predictions is enough to tackle a basic science project. So anything that we're looking at in this course, it's going to be like 1 prediction. So 1 if-then kind of statement, keep it simple, but other things become more complex as you build and grow and as questions aren't so easily answered. But I don't want to go past this without any examples to make sure and what you can build from. As these are ones I'm pulling from another website, but if we start with the question, how does the size of a dog affect how much food it eats? It's a question, it's a how, it's a process. And you kind of see a cause and effect. You have to look for the first event that would precede the next event. So here it's saying, well, dogs eating and their size, the size of the actual dog is the preceding cause event that you have happening here. So that big ass dog or that little dog or whatever size is eating, and effective like how much food do they actually eat. So overall, when they're eating in the beginning with that, how much do they end with? So there's a cause and effect within it. It's beginning that it's something that's measurable because size of dogs, you can think about their mass, their height, which whenever is which best, probably mass themselves. And then the food itself, you can say, well, how much they eat? That's also something that's measurable. Is it by how many cups of food did they have, or also weighing and having mass of food before and afterwards, and then actual change as well. Who knows? So hypothesis that you could build out of this, and there's others. There's many other hypotheses that can come out of that beginning question, and that's not the end of it. We're just discovering and building on that pool of knowledge, say, around size of dogs, eating, and food. And if you have dogs, you probably have some pre-research already built into your head, your lived experience of having those dogs. And if you don't have dogs, well, then you'd have to research then around what has been gathered about their eating patterns and how does this affect stuff, blah, 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 metabolism, energy, all that kind of stuff. And then you become into a little bit more of your actual hypothesis. So this example here, it's like larger animals of the same species expend more energy than smaller animals of the same type. To get the energy their bodies need, the larger animals eat more food. So here you can see more pre-research, and they're being a little bit more specific. I'm not just saying other dogs, but keeping the species type together, if that's something that could actually have an effect in between the two, cats, dogs, in between families. And this also tying to then to the energy their bodies need. So by probably pre-research, larger, probably need more energy to run that larger body, so they will need to eat more food to run it from there. Maybe that's the pre-research that they found. And now the predictions, here you can now see, so hypothesis, you can still see the cause and effect, that their size within it and having their food, they just added more knowledge of the energy and all the rest of it that's needed. Now the prediction themselves that they built off of this is that, maybe like they went more specific. They didn't just keep it general saying size of dog. They said specifically what size. And this is stuff that maybe you don't need to go to this level for predictions, and maybe it's built into your experiment later on, but this is where you can see them going more specific right now, earlier on within the actual phase. So if I let a 70-pound dog and a 30-pound dog eat as much food as they want, so you can see the cause, size of the dogs. They're also building in some of their pre-stuff for their actual experiment. They could have just said, if I let dogs eat what they want, and then in the design of the experiment, when we come to that as part of the procedure, they said, I will have a 70-pound dog and a 30-pound dog, and state it later on. They didn't have to do it here, but they're including it earlier on, but you still see that cause. They have then, after the then part follows the effect, is the 70-pound dog will eat more than the 30-pound dog. And this is very specific then, because based upon the measurements, if we find out afterwards that the 30-pound dog, the actual numbers and empirical evidence we gather that the amount of food they ate in the same conditions that the 70-pound dog had, then okay, and that's something we can start building off of. Now you may be asking, okay, there's probably other things that are causing this and other things that could say that this is wrong and say this is just, think of this as just an artifact, and this is the beginning point. We'd want to wait till they're later in their argument, see how they set up their experiment and came to the conclusion. And if we can poke holes in it later on, we'll do that later on, but for right now, you can just see their cause and effect. Now, another one, if we go through this quicker, is does fertilizer make a plant grow better? So fertilizer, first cause being added to the actual plant, and then the plant growing better in some way afterwards. Hypothesis, plants need many types of nutrients to grow. Fertilizers add those nutrients to the soil, thus allowing plants to grow better. So you can see still in depth, they've added more knowledge to that. And then finally coming to their prediction off the hypothesis is that if I add fertilizer to the soil of some tomato seedlings, but not others, and then the seedlings that got fertilizer will grow taller and have more leaves than non-fertilizer ones. So these are things that are still all very measurable. You can see them there designing the experiment into it again by saying specifically the plants, not just any plant, because tomato plants versus corn to flowers, everything's kind of different from when it grows. And they probably would have gathered that in their pre-research or lived experiences that they have. And then they talk about things when they say, okay, grow bigger. They define it better by saying things like, okay, we'll have more leaves. We'll grow taller and have more leaves than non-fertilizer ones. So they can count the leaves specifically from the plants. They can say it grows taller. It's something that's measurable from there. And again, this is where you could have different hypotheses, different predictions. If you were to design this, and maybe this is where you innovate, that you saw that, oh, well, that's the hypothesis and prediction they had. What if I change that? What if I change the prediction and I innovate? So building off their knowledge, I innovate, change it slightly, and then see what happens and see and grow from there. These ones I won't go through, but you can go back to the slides yourself if you want to get more examples that maybe you connect with a little bit better. Now we're back and we can see the overall chart that we have, again, asking a question, doing the background research, and then constructing hypothesis, so that testable tentative answer without presuming truth from it that we want to test. And we would have then built the predictions, those if-then statements coming off of the hypothesis before we go to the next step. And so we're going all within this order. Maybe, again, we've decided that we cancel it now and we change stuff as we go before we go into the experiment. Or we have to do more background research before we can continue because we're not sure about some of the next steps. But we've done these 3 kind of general steps. And then from there, we want to systematically move to then the test with an experiment. So we need to take that hypothesis and we're going to actually design, set up steps for how we're going to do that experiment. So maybe it takes more background research knowledge, set up, gathering your tools, your materials, recording all of this and making sure to communicate it later on so other people also know then how to repeat what you're actually doing from there. So what is an experiment? So here's a very sciencey definition. So again, I say this here because I'll dig deeper down to this and give other definitions, but this is an important one to start with and realize, okay, well, what new terms does it add to our understanding and knowing? And we're going to dig deeper into this definition, especially when we go to scientific method part 2 and part 3 and everything else. But I want to give that general overview. So what is an experiment? So again, 1, it is a thing that you're using to test your hypothesis and your predictions. 2, it's where you're gathering your empirical evidence, that measurable observations that you're going to analyze later on to back stuff up. And it's based upon your hypothesis, which is also then this whole step of everything before this of the question, the research and predictions and hypothesis is based upon the cause and effect relationship that you are looking at. And we're going through these steps to establish causality or that causal relationship that we think we see between those two events. And if we think we see it versus the evidence show that, hey, this seems to be stronger than other people, then maybe we're coming to something else we can use to innovate and change and understand our world. And we've gone through the steps beforehand. So here, what is an experiment? So I'll do it in a very sciencey voice and very monotone to add to the definition. It is the manipulation of variables under controlled conditions in order to infer cause and effect relationships. Wouldn't it be horrible if I did the whole video in that voice? I'll try to throw in some other more interesting voices as we go through all of this. It may become more natural at the videos. So with that definition, we're going to have to dig deeper. You have to remember that's empirical evidence. We're doing measurements. There's numbers that are involved with this and units. So we have the idea of variables, that manipulation and this change in quantities and amounts. Controlled conditions is that we're trying to set up and remove other things that could be extraneous, confounding things that we don't want to have there, that we want to keep things very consistent, and so that other people can do it. And that if other things that are out of our control, maybe that's really what's causing an actual problem. We try to do our best here. This is not always easy in every experiment you do. You acknowledge if you're not able to, but if we're doing basic ones, you want to see, well, how do we keep that the same, and trying to infer that. So an experiment is a procedure carried out to support, refute, or validate the hypothesis. So again, saying the other way, and saying the word procedure. So just like the scientific method kind of steps, is that an experiment is also steps, and it's something that you need to design first. You don't just randomly go into it after hypothesis. You design, you work out the steps and how you're going to work out that procedure. And then once you have that worked in place, then you follow that procedure like a computer or anyone else, and you're just, okay, I go through these steps, I gather the data, I follow the procedure of what I've done. Or I give that procedure to someone else, another researcher or a research assistant, and they go through gathering and doing that data and that work for me or as a member of the group that's working on the actual project, and they follow that actual procedure. Maybe someone else follows the procedure to repeat it, that's a different person, but they follow the same procedure and getting the data and then analyze the data from those actual steps. Okay. So experiments provide insight into the cause and effect by demonstrating what outcome occurs when a particular factor is manipulated. So here's the cause. Maybe that's what we're looking at, the cause preceding it. We manipulate things for the actual cause that we think is tied to the actual effect. And so manipulating here again means quantities, numbers. So if we've thought about them being measurable, we change that. If it's the dog example, so size of the dog and eating that, then the size of the dog is the thing that we're manipulating. There's still the dogs. We get dogs of different sizes. Right there. Keep it controls. Maybe we try to keep them around the same age, because maybe young pups versus older dogs eat differently, and maybe the amount of food they eat wasn't the size, but it was the actual age. So maybe we'll try to keep the dogs roughly around the same age group. From there, we try to then manipulate and say, okay, well, I'm going to have bigger dogs at 70-pound and that 30-pound dog, and then we're using pounds as a way to indicate the actual mass, and we're changing those. And so having those factors, maybe multiple dogs, and that's how we manipulate. We have maybe like 10 dogs at around 70 pounds, 10 dogs at around 30, and 10 smaller dogs even from there. And then seeing the teacup poodles, all that, and seeing like, yeah, well, what happens? That's the manipulation. And then seeing, well, what is the effect afterwards? And then measuring that actual mass of food that's gone. So, like, that's procedure. And they vary in scale and how much work it actually takes. But in the end, it's just that logical step of sequence of steps of one after the other to analyze and gather the data. And from this point, you're going to be following the procedure and gathering a lot of data. So again and again and again, and measuring that, and then using that data, all those numbers and all those measurements to actually then calculate stuff. And this is where we're going to get the statistical reasoning and kind of the stat skill, which is going to be the most of the math that we do for this version of the course. So your experiment tests whether your prediction is accurate and thus your hypothesis is supported or not. So you've got the if-then. You're going to be gathering and going through your procedure, gathering your empirical evidence, and then based upon that evidence, coming to a final conclusion of, okay, looking at the predictions, the if-then, okay, yes, this does accept it. Now, that yes, this does accept it statement is very vague, and when you're getting to math stuff, it's going to be more specific. And you can see in stats, we'll get deeper down to that, and if you go deeper and deeper into stats, and I was using science, you get that question answered more in a calculation and quantitative reasoning to come to those conclusions. That's also agreed upon by the general science culture. So, yeah, and so is hypothesis support or not, it is important for your experiment to be fair test. You conduct a fair test by making sure that you change only one factor at a time while keeping all other conditions the same. And this fair part is maybe trying to remove a bias. What if the question, the outcomes from this research is very important to you? Maybe it results in more money, more results, or something else better. And you have to show, well, how did I remove my personal bias and other conditions that could be having an effect from it? And this is going to be part when we get to the design of the actual experiment. And when we get to scientific method part 3, we'll dig deeper into that a little bit. We're not going to be experts by the end of this course. That's not the goal. You can go on to other science courses if you so choose, and whatever other course seeing like how is that actually done within that field itself. But it's going to be keeping that controlled kind of scenario is going to be very important. So during the experiment, you will gather your empirical evidence that will later be analyzed. So I've said this again. Remember, empirical evidence is that measurable, observable, like data that you're gathering that's separate from myself, that someone else would also be able to come to similar measurements based on if we agreed upon how things are measured and what are the units and what tools are actually used. So it's key that you're also communicating this in the way that, like, in whatever way that you're communicating this across is in your argument. You've said how you're doing this. You should also probably repeat your experiment several times to make sure that the first results weren't just an accident. Maybe it was just a chance that this happened. Sometimes this repeating can be done by how many samples you do. So the population, say maybe how many dogs that you had. So you don't just have 2 dogs. Maybe you had 10 dogs. Because just one of them, maybe there was something else with that dog was different, and you want to include what is sample or pool. But we'll talk about this a little bit more when we get the statistical reasoning notes later on. Now here's another term as being an experiment procedure, something that you want to write up. It's also, you can see at the top, just as a quick reminder, you can see you got the header that says Scientific Method Part 1 Questions. It means there is also then a question document associated with these slides, and in saying here that, hey, this stuff is probably good for questions 5 and questions 9. And again, those questions aren't worth marks, but it's a good way to keep up with notes. It's a good way as you're going through these notes in these videos is just answer those questions now as you get in here, and then later on when you come to the tasks, the assignments, and the exams, you can refer back to that material and your notes as extra review. So again, an experiment procedure is a step-by-step recipe for your science experiment. How will you manipulate the values for the cause and then gather measurements for the effect to gather your empirical evidence? And this will include recording a lot of actual data you'll keep in tables and something else. It's not just one or a few numbers. Usually this ends up being a lot of actual numbers and a reason why you need the actual stats later on. Before jumping too much further, is giving maybe a very, very basic example, basic cause and effect relationship, maybe something you would see for an earlier science fair in like elementary school or so. But it still kind of shows the steps and showing this systematic procedure of what you can do and what you would need, that you would design this and include this in your write-up. Sometimes this is more like, it's not this detailed because it's known in certain areas like psychology or others that this, when you say this type of experiment, this is how it's being done. The procedures are already documented. So example here, what if we had a procedure to testing different brands of batteries? That we had batteries, say AA's, 1.5 volts, and we wanted to see, does the brand actually cause a difference in the quality of how long the battery lasts? So is there a difference between brands? It may be whatever they're made. It may be like the Energizer, Duracell, whatever brand you're actually going for, and testing this and seeing, okay, which ones are the actual better ones. I'm going to quickly go through this. I won't read everything. You can read it yourself in the notes. I'm not going to make you memorize this. This is just to give you a feel if you want to work out an example, or say if I ask you for an example in a test or a task, you have to write up that I want you to give me this feel of these actual overall steps. And please don't just regurgitate this slide back to me. That's not going to help show me your understanding of it. So say, step 1, number each battery so you can tell them apart. So you may have other overall brands. Maybe here you also you hide the brand, because maybe that's a bias that whoever's gathering this, they've always used Duracells, they like them more or something. If you have a brand loyalty from right here, so maybe you number them, you make sure that there's no logos and they just all look the same size, all AA from right here, and you can tell them apart separately. And then with each one number, you can record that and say the measurements you got for that numbered battery. Measure each battery's voltage using a voltmeter. So this is another tool. If you don't know what a voltmeter is, you can go look it up. But just something for gathering what is the starting amount of actual volts they start with. Is it slightly varying off what they get? And you record that for each battery. Put the same battery into one of the devices and turn it on. So here you'd have to list what type of devices you're using, brands, and everything else like that, because it can all have an effect on how much energy they draw from the actual battery. Later on steps, they talk about that a little bit. Let the device run for 30 minutes before measuring its voltage again. So here they're saying specifically a constant, keeping the same. They're not varying how much the device is used for. They're saying, okay, time is one thing you're measuring that can have an effect. So all of them, the batteries will run it for 30 minutes, long enough that it should be depleting the actual overall energy within it. And record the voltage on a table every time it's actually, so every 30 minutes you keep doing this. And here now, you see, don't just take one measurement. Step 4 is let the device run for 30 minutes before measuring the voltage again. And step 5, repeat step 4 until the battery is at 0.9 volts or until the device stops. So here they're basically how long can it run a device on that actual battery. They're keeping that consistent, saying the time. They're measuring and getting lots of measurement over the time and see how does that change, how does it deplete. And then even step 6, do steps 1 to 5 again, 3 trials for each brand of battery in each experiment group. So it means, okay, well, they'll have, if Duracell is one group, they'll have 3 batteries from Duracell. They'll number it. They'll go through each one for the actual measurements here. And then they'll repeat that 3 times. They're not just doing the measurement 1, they're gathering that data. Then they're doing it again for the rest and the rest. You see, there's going to be a lot of data overall that's gathered, and that's going to, again, the basis of your empirical evidence. The rest of the steps here, they just give it more specific. So you can see that kind of steps of what you're doing and what you'd want to actually include in this procedure. And so maybe this is part of your background research, or you're doing extra research into these kinds of things if you don't know enough from the beginning, or asking someone else who has more experience with it and building off of there and building a procedure. Now, once this procedure is actually done, then we want to document that in whatever way that we're doing it right up in the end. And then we're going to go through actually gathering the actual data. And so you can see, again, asking questions, doing the background research, construct a hypothesis, making your predictions, designing your experiment procedure. You go through running the actual procedure and gathering the actual data. And maybe you've got to troubleshoot the procedure, is that when you're actually executing it, maybe you realize something's wrong or something comes up. And so maybe at this point in time, you're like, okay, the procedure is not working. Maybe I stop going through it because I've noticed something while I'm doing it. And I go back and I carefully check all the steps and I fix things up from there. And then, or if it is working, you just, once you're done running the procedure and you have all of the actual data, then I go in and actually analyze it and draw conclusions from that actual data. So this is where your quantitative reasoning and the stat skill are going to come into play, is that once I have those actual numbers, okay, then what conclusions can I actually draw from it? And your stat skills will also come into play when you're doing the experiment procedure, because picking how many samples you have, trying to design that procedure to minimize other effects. This comes from understanding stats properly. And that's what you'll see later on. Before we go into scientific method 3, I'll be going over notes for statistical reasoning and understanding good and bad parts of stats, understanding the actual tools. And once you understand this, this is part of that background research to help you design and then analyze what you're actually doing. Okay. So analyzing your data. So we're coming up on the slides. You got to be feeling some joy as I talk forever, as it's been about 57 minutes so far for this, and then we're coming near that end part of these notes. So once your experiment is complete, you'll collect your measurements, empirical evidence, all of it, analyze it to see what's coming out using, again, repeating myself, your critical and quantitative reasoning. And so remember, again, the quantitative reasoning is using, based upon some specific context, using some kind of actual math and a real world scenario, coming to some actual conclusion. And so you have to look at the overall, what is the cause and effect you're looking at, what is the context, what is the environment you're with it in, what tools are you actually going to use from your math skills, doing calculations, looking at the actual numbers, and then based on all of it, coming to a final conclusion. And all of it's important. So scientists often find that their predictions were not accurate, and their hypothesis, and i.e. their predictions, was not supported, and in such cases they will communicate the results of the experiment. Maybe they internal lab report, or you record it yourself because you know it, and it doesn't mean it's the end result from there. It means, well, maybe that becomes more of my background research. Now that I know that this didn't work and it's not supported strong enough, I at least know that information, and I can go back up and maybe construct new hypotheses, do more research, make new predictions, and redesign the actual overall experiment and get it to grow from that point in time. So asking new questions, innovating off of what you've known. It's not a failure. It's just new knowledge that we can't say is supported long enough to distribute widely for an actual community, other than to say, okay, well, this is what we've shown that this didn't work. And then other people and yourself can grow off of that. So they construct new hypotheses based upon information and learn during those actual experiments. This starts much of the process of the scientific method over again. Even if they find that the hypothesis was supported, they may want to do more tests and make it better and build off of that. Possible new innovations, new ways of what we're doing. And so if we're looking at augmented reality or whatever you're looking at, you have a question. You think, okay, well, this is something I think could actually have a benefit, maybe change the world. And I think this is a cause and effect, and I want to test if this will actually work. Augmented reality being used in education, and does it help people learn better if it's used? The cause and effect, using augmented reality, learning better. And Maybe that's a new possible innovation. Maybe you found things did work or didn't work, and you can start building off of that. Last part, once you feel that you've analyzed it, and if you've gone past the phase where I can say, yeah, this has been strong enough and I can make my actual overall argument, you want to communicate these results to others in some kind of final report. There's different ways. Now, if we're doing this from a science culture, there's some key things nowadays of how this is actually how you go about doing that in modern day 2020 or so. If you go way back in history, how it was accepted was completely different. Right now, professional scientists do this by publishing their final reports to a scientific journal, by presenting the results in the form of a poster or paper or a talk they'll actually do. And it's not just that I finished this and it can automatically get accepted, as I would generally do this write up. I would write the report in a specific way that's acceptable for that actual journal we're looking for, which is it's a publishing body with other science people, and I would then submit it to it. A committee would then review it, and that's kind of blind, that they don't know it's me and I don't know it's them, and they have different reviewers, and then those reviewers give feedback, and a committee then makes a decision to accept or reject this. And it's not always perfect, and you're hoping for the overall best, but it's a different process you're going through. And if it's accepted, then it gets published in that journal, or for those conference proceedings, you generally then go and then give talks in front of people, so you have a chance to hear what other people are saying and seeing what's going on within that actual culture. Kind of like a forum you could think of in a city, or a big ass coffee shop, where you're sharing this and you're having it being critiqued, coming back, and maybe being inspired and connecting with other people and building more of a cultural community communication of what you're doing and communicating this. Okay, so as I said, I kind of like to do things in threes. We had that short video in the beginning, which talked about the scientific method itself and gave you those basic steps. And here I found another video that also graphically draws some of the steps better, goes through all of them, and it gives some extra, when we're going through this, remember, take it as a review. What did we just go through the steps? Okay, what are they saying? Get that locked into your memory a little bit more, take down some notes. And it also goes into a little bit extra things about terms like correlation and causation with causality that we'll be talking about later on in the course, but become very key terms that help us dig deeper into the scientific overall method. So while watching this video, take down key terms, see how, who's attributed with the knowledge, some of the historical background, some of the key terms that are brought up, and things that you're okay, well, that's important that I've seen now, and how do we dig deeper into that and make our understanding stronger and show our own personal connection to the actual knowledge and our growth from it.
Why are some kids sad? What makes the wind blow? How do birds fly? Our world is full of curious phenomena. To find answers or solve problems, we can use a process which was first acknowledged by the scientist and philosopher Ibn al-Haytham in the 11th century. Also known as Alhazen, he is considered to be the father of optics and the scientific method. There are 6 steps to it. 1. Observe and ask questions. 2. Research. 3. Formulate a hypothesis. 4. Test your hypothesis. 5. Conclude. 6. Share results. The goal of the scientific method is to find out the truth. Let's try. Step 1. Observe and question. Observation helps us formulate challenging questions that you will be able to test. A good question converts the natural sense of wonder into a focused line of investigation. When is the best time to drive to school? Which food is my dog's favorite? For example, if you observe that women smile more often than men, you might ask, why do women smile more often? Step 2. Research. Find out if other people have asked the same or similar questions. If you research online, use search terms like study, research, or meta-analysis, which is a summary of research for a specific topic. Read as much as you can about your particular subject to see what you can find out about. For example, research happiness based on gender, or study the science of smiling in different cultural contexts. Step 3. Formulate a hypothesis. A hypothesis is a theory that you can test to see if your prediction is right or wrong. From your observation, you have noticed that women smile more often and that people who are smiling seem to be happy. From your research, you know that there are different types of smiles: shy, genuine, and false. In one paper, you read that baby girls smile more often than baby boys. Here is a hypothesis. Women smile more than men because they are happier than men. Step 4. Test your hypothesis. When you test your hypothesis, you want to make sure to do this in a fair way and that the conditions are constant. For this hypothesis, we can design a test where an interviewer talks with a set of men and women for 5 minutes each, counts how many times they smile, and then asks each one to rate their level of happiness. To get a good sample of the population, we invite 300 women and 300 men. Seems like a good test, right? But wait, what if the interviewer is a woman and men tend to smile more at women? Or vice versa? Or what if the topic discussed is one that interests women more than men? And what if people aren't reliable reporters of their actual level of happiness? So clearly, we would need to be much more careful. Step 5. Analyze and conclude. Let's assume that you designed a very careful experiment, controlling for as many variables as possible. Now you can analyze the data to see if your hypothesis is correct or incorrect. Depending on your findings, you may want to change your hypothesis or change the design of your testing. Perhaps you have discovered an even more interesting question. This stage of the scientific method can be repeated as many times as necessary until you find just the right hypothesis and test method to find accurate results. Step 6. Share the results. When you are satisfied that you have proven or disproven something important, report your results. In science, it is important to detail your methods so that your peers can review your work, which is a critical step to getting published. If your results are solid, your experiment can be repeated by other scientists. Such reproducibility is a sign of good scientific work. But failed results can also be interesting. An incorrect prediction could prove to be important and should always be reported. To make sure you get it completely right, here are 3 more things you can check before you publish. A. Any scientific theory is falsifiable. Real scientists know that there is no such thing as a scientific proof. In other words, you can never prove your theory to be 100% right. All you can do is find a lot of supporting evidence that it could be correct. Here is one example. Say that someone says, hamsters can fly. We cannot prove that this is false. Yes, we have never seen a hamster fly, but we can't test all possible conditions or look in all possible places on the planet to know that all hamsters never fly. Maybe a space hamster does. So while we can often prove that a phenomenon exists, it's much harder to prove the non-existence of something. If your theory can't possibly be proven wrong, then it's not falsifiable and hence not scientific. B. Correlation is not causation. When you analyze your results, it is important to separate between 2 possible reasons: correlation or causation. Let's say you hear that towns that have more churches also have more bars. Could it be that religion makes people want to drink, or that drinking helps people to find God? If you add more facts, such as larger towns have both more bars and more churches, you can see that a larger population is a more likely cause of higher numbers of bars and churches. There is probably a correlation, but no causation. If we compare men with women and would conclude that women smile more and are more happy, then this still doesn't mean that it's happiness that makes them smile. Maybe they just eat more chocolate and cookies, which makes them both happy and smile a lot. C. Avoid selective windowing. When you publish, you've got to show all relevant facts. Colgate once ran an advertising campaign claiming that 80% of dentists recommend Colgate. What they didn't tell us is that when they asked dentists to select their preferred toothpaste, Colgate was just one of many other brands they also recommended. Colgate was later sued and forced to take down their misleading ads. The purpose of science is always to find out the truth and nothing but the truth. To use science to mislead us is wrong and terrible business practice. Let's do a last example together. I have 2 coins. One is bigger. Why? The small coin says 1 cent, the bigger one says 5. Aha! Small coins are worth less money. Bigger coins are worth more money. I pull some more coins from my pocket. 2 more pennies, 1 more nickel, and a $0.25, which is 25 cents. Great! My hypothesis seems true. But wait, is the quarter worth more because it is bigger? So is that a correlation or a causation? My sample size is pretty small. I don't think I am ready to report my results. Can you help out? Please apply the scientific method to study your local currency. Maybe you have a hypothesis that we can test until we get solid, repeatable results to report. Please publish your findings in the comments below.
Okay. I think that's a good review, and it gives you some knowledge for future stuff that we will deal with. Definitely the correlation and causation and your sample size and all of that. That will become in multiple notes within the future. So let me just end by going more full screen. So I hope everyone, you enjoyed these notes and somehow I didn't put you to sleep. What, an hour and 12 minutes so far? And so it's a good idea. Make sure that you've gone through this material, like even just looking at the slides, maybe going through this video again and watching those videos and making sure that you feel strong about this. Like maybe list down stuff you feel unconfident about and you can bring that up in class or the online review, whatever way that we are communicating when you're watching this video. I go back to that questions document. Again, let's go through like how could you answer those questions? Do you feel confident enough to answer those? What notes would you take down? And if you do this as you go through all the notes, it's going to make your life a lot easier for those future tasks and those future exams. Other than that, I still hope you're doing wonderful and try to do something nice for yourself or someone else. Maybe make this world a little bit a better place.